Hello everyone, my presentation title is Linear Attack on Round-Reduced Depth using Deep Learning. Block cipher is an important member of cipher algorithm. Different with other ciphers, it will greatly divide plain message into several blocks and handle each block with secret key held by sender and receiver. Due to the special structure, block cipher runs very quickly and are widely used in our daily life, such as in IP protocol, SSH, and so on. Of course, security is its most important topic. To now, lots of work have been done to analyze the security of block ciphers, such as differential cryptanalysis, linear cryptanalysis, integral cryptanalysis, and so on. Those analyses greatly improve the development of cipher design. And linear attack is an efficient non-plaintext attack in them. Linear cryptanalysis was first proposed in 1994, and from then, it has achieved successful attack in many round-reduced block cipher in recent works, and there show some main results. Though linear attack is a very efficient tool, there are also some problems in real application. First, the analysis process of cipher are very boring and requires deep basic of math and cryptography. Second, as for researcher, they often need to promote the analysis of many cipher at the same time. Third, industry need to design, analyze, and select different ciphers for different application frequently. Therefore, for block cipher, exploring some automatic analysis scheme has become a hot spot of people's research, and many typical schemes such as MILP, SAT are proposed. These automatic analysis methods can reduce the manual burden to a certain extent, but also bring problems such as high space-time complexity, the need for an amount of professional software. So people began to explore some other solutions to enhance the intelligence of cryptanalysis. With the growth of computing ability and the development of application of big data technology in recent years, deep learning has gradually made great progress in many fields of artificial intelligence, especially in fields of machine translation, automatic driving, computer vision, and so on. Its excellent performance makes deep learning reach advanced level in these tasks, and even surpass human level in some tasks. Those reflects the strong learning ability. In a word, deep learning essentially provides an end-to-end, more fine-grained feature extraction and discrimination tool. Combining the powerful feature extraction and category classification ability of deep learning model with the classical linear cryptanalysis method for block cipher algorithm is our main motivation. We hope deep learning technology can replace some phrases in linear cryptanalysis and achieve linear attack on block ciphers using deep learning, trying to explore some surprising conclusion. So in this paper, we use deep learning network to achieve linear attack on round-reduced depth with plain cipher pairs. Comparing with traditional linear attack algorithm, our work requires less knowledge about complex cryptanalysis, as neural network can work well by data-driven. And we are the first one that uses neural networks to achieve non-plaintext attack on complex block cipher. Our work are based on DAS, one of type complex cipher. DAS was contained in National Bureau of Standard in 1977, and our discussion on it is representative. DAS is an iterative cryptography algorithm, and with phase-toe structure, which has profound impact on design of later ciphers. It contains exclusive OR, cycle shift, permutation, and other operation. S blocks in each round realize nonlinearity. A linear approximate equation of required round is the core of linear attack on depth, which is used to describe linear relationship of bits in several fixed locations. Those locations bring in plaintext, master key, and corresponding ciphertext. For example, there is a 3-round linear approximate equation. It will include 12 bits for given random plaintext and the corresponding ciphertext, and the probability of it holds is about 0.7. Based on linear approximate equation, we can achieve 2 key recovery attacks, 1-bit key recover and multiple bits key recover. The approximate equation in 1-bit key recover only contains elements in plaintext, ciphertext, and key. So if the probability equation holds a big bias with 0.5, given plain ciphertext pairs, we can recover 1-bit key, 0, 1, with high successful rate. Also, extend the equation with Xbox function f, we can obtain a plus equation contains elements of subkey more. Given plain ciphertext pairs, we need to test all possibility of bits in subkey and check the probability that the equation holds, so that we can determine multiple bits in subkey. We plan to apply deep learning network into key recovery process so that replace manual analysis. There are several difficulties needed to solve when apply it directly. First, traditional key recovery algorithm is not suited for network. We have to change it. Second, the output of key recovery will not satisfy the equation absolutely, and there are in fact 2 different distributions. Our network must obtain the capacity to discriminate them with each other. Third, as the equation contains XOR operations, our network must learn them well, so we propose our attack architecture. First, we design 1-bit key recovery architecture, and there we represent the linear approximate equation. Traditional key recovery algorithm requires full information of equation and plenty of counting operations. After a given number of random plain ciphertext pairs generated by same key, we should extract each pair into the bit sequence, then rely on the equation. We need to XOR those bits and obtain the 1-bit key guess. Count them and judge the value of key bit. The correct rate is equal to the probability that the equation holds. In our deep learning network recovery algorithm, the process will be quite simple. Give a number of random plain ciphertext pairs into trained network net discriminator. After extracting pairs into bit sequences, the discriminator will output result guessed of key bit, and we can predict possible 1 bit by counting up those outputs. There we can see that XOR each bit in sequence and find a relationship with its core value, and key bit is our neural network do. Thus, in order to satisfy those requirements, we train by those ways. There, we used to present n-round linear approximate equation. Receive bit sequence extracted by linear equation. We pad left side into fixed length and set the right side of as label. We choose residual network as our main iteration layer in network architecture, as this network has been successfully applied in many domains. It consists of some residual blocks which add into a layer and output layer and produce new output. The output will be sent to new block. The most important advantage of a residual network is that it can effectively avoid gradient dispersion when the number of layers increases, and we call each layer as one depth. Pay attention to the labels, because label is special. The label is generated by the red cipher as it not hold all the time. For the same label, there are two possibilities of XOR value operated on input sequence 0 or 1. The appearance probability of them can be almost described as binomial distribution, and for another label, the distribution will inverse. We show them in this page. Thus, our network in fact needs to distinguish two different binomial distributions. So the total process contains three phases. First phase, data generation. We generate data tags and master key ordering uniformly distribution, and encrypt plain text with random key by n-round dash cipher, and obtain cipher text. There, the key of each plain cipher text pair is different. Then we get bit sequence through extract text pairs, depending on linear equation. Second phase, model training. After padding those bit sequences, we fed them into network with label relying on XOR value distribution of each 1-bit key. In each epoch, we will check networks by validation data, save and update the best model according its accuracy. Third phase, key recovery. Trained model will be used in 1-bit key recovery algorithm. We judge key bit according to the output of the model. As for multiple bit key recovery, it is quite different with the single 1-bit, because those are several bits in subkey, called effective subkey bits. N-bit effective subkey can set up arrangement, and we have to search those possible key candidates and test them to determine the most likely candidate. So key recovery algorithm will score each candidate according to the prediction of network. There we use to represent the n-round linear approximate equation. Due to the existence of Xbox function and the effective subkey bits are not determined, we can use the difference of labels data distribution directly. In order to simplify our model, we suppose that value of gamma times k is 0, which may happen with a probability of 0.5. First, we generate plain text p and label y, ordering uniformly distribution. Then, we generate master key k, ordering uniformly distribution. Ensure gamma times k equals 0. Later, encrypted plain text with key by n-round dash cipher and obtain cipher text. According to the approximate equation, pairs will be extracted with the order of plain text, cipher text, f1, fn. But for each label, if the label is 0, fill the f1 and fa number of uniformly distribution. Thus, the XOR value of our data have two different binomial distributions. In one, the 0 appear with probability of 50%, and in another one, 0 will appear with the probability of equation holds. We hope our network can distinguish those distributions. First, we tested the performance of 1-bit key recovery algorithm. Our model was trained for 200 epoch with a batch size of 1000, and the size of trained data is 1000 and validation data is 10,000. The model performs well, and the picture shows that the accuracy on validation data is 67.23%. It is very close to the theoretical value, which is 70%, and both validation and training data perform synchronously, indicating that network work well without overfitting. We use trained network to recover 1-bit key by proposed algorithm, and find that it can recover key information with the successful rate more than 99%. We increase the number of plain ciphertext pairs into 64. With thin pair number, the successful rate of neural network model is only lower than the traditional model slightly, and increasing the number of training data, neural networks will work better. 1,000 training data can improve accuracy with 0.43% than 10,000. Expected 3-round 1-bit key recovery. We also run 4 and 5-round key recovery. Comparing with L3, the binomial distribution probability like PL5 even decreased from 17% into 51.9%. Obviously, the difficulty of distinguishing those different distributions increases a lot. This table shows the accuracy and key recovery for best model. For neural discriminator, though it does not achieve successful rate more than 95% with less than 20,000 pairs plaintext ciphertext, it still performs its ability recovering key bit with successful rate of even 90%. In order to achieve multiple bit key recovery, we train 4-round neural network with 20 epoch, and each epoch run in size of 5,000. Real and random data determined by random label were sent to file-depth residual network. The training set is generated by a random master key, which holds gamma times key k equals 1, and those two different distributions were separated with accuracy of 56.77%, while the accuracy of theoretical traditional model should be 58.3%. And there are 6 bit key, which means that 64 key candidates in key ranks. All of those key ranks are lower than 32 and indicate that our neural network model can distinguish different distribution in multiple key bits recovery and pretty effective for key ranking. In this paper, we use deep learning network achieving linear tag in round-reduced depth. We propose the network structure to distinguish different performance of linear expression. Our experiment indicated that those deep learning networks have the capacity of learning complex static characteristics like XOR and distinguish different distributions. In order to make neural network perform better, we also designed 2 linear tag algorithms, which apply network in 1-bit and multiple bits key recovery. Those end-to-end architecture need almost few knowledge about distribution of linear expression and performs well in our experiments. And the representation of our results are also useful for cryptanalysis on other more complex block cipher. That's all. Thank you for listening.